Principal component analysis is simply the statistical interpretation of the SVD. And that's the video. Okay, let's explain it more. First, let's make a deal. I want you to think of matrices as transformations, not data holders. As you can see, an orthogonal matrix multiplied by a vector results in a rotation of that vector. And for a diagonal matrix, it simply stretches or scales the axis of that vector. So now, multiplying two matrices is simply combining two transformation sequences. Our goal in PCA is to find directions that maximize the variance. That's what you hear in all the videos and books. When we project a three-dimensional data into two axes, it will result on data with two dimensions. We want that, but also to keep as much information from the original 3D data, with the ease of interpretation of 2D data. The first step of PCA is to center our data matrix, so all our variables reflects the true variance and not the mean. And now, to find those directions or principal components, we want to take a look at the covariance matrix of X, given by this formula. The covariance matrix contains the variances on the diagonal and off diagonal the covariances between variables. After centering the data, the covariance matrix is proportional to this. So that's our covariance matrix. The eigenvectors of the covariance matrix are the directions or the principal components. Why? Because the eigenvectors of a matrix is a direction or a vector that the matrix does not rotate, only scales its length. Here, thinking of matrices as transformations helps us understand why eigenvectors are used as principal components. And if we want the components that preserve the maximum variance, we look at the eigenvectors that the matrix transformation stretch the most. So, how do we obtain those eigenvectors? Ever heard of singular value decomposition? It's a method that decomposes any transformation X into three simpler transformations: rotate, stretch, and rotate again. With U and V being an orthogonal matrices and sigma a diagonal matrix. Performing the SVD on our X matrix results in this. Multiplying it by the transpose to get the covariance matrix results in this formula. If you notice, this is the eigen decomposition for the covariance matrix, where the matrix V contains the eigenvectors as columns, and the sigma squared is their eigenvalues. It's interpreted as how much each component explains the variance. So PCA simply uses the singular value decomposition and then takes its right singular vectors, which are in matrix V. After finding the components, the last thing is to project them on our new axes. Now the projection process is easy. We have the V matrix being a projection transformation combined with our data X. It rotates the data into the principal components coordinates, which are given by simply using the SVD. Since V is an orthogonal matrix, we can do this, and U times sigma are the coordinates for the principal components. This transformation also diagonalizes the covariance matrix for the projected data, proven by simply calculating the covariance for the projected data, and it will result in sigma squared, which means that each component is uncorrelated with others and preserve the maximum variance. And yeah, I said that a lot. So SVD is simply all-in-one pack to solve the PCA and interpret it. Check this video about singular value decomposition. It's very helpful for the intuition. That's all. Thanks.